Last but not the least, by the way, next slide, please. Yeah. Last but not the least, I'd like to invite my colleague, Elze Swinkels. Elze is a deep learning engineer here at Delft, and today she will discuss about AI-driven lung abnormality detection, especially about designing a point-of-care ultrasound screening solution for it. The floor is yours, Elze.
Okay, thank you, Katja. I would indeed like to tell you something about a new project we at Delft have been working on over the past 2 years, which is about using ultrasound assisted with artificial intelligence to detect lung abnormalities. Sorry, I'm having some problems going to the next slide. Yes. So we think that this could be a potential solution for screening and triaging lung diseases, among which tuberculosis, directly at a point of care. But then why would we use ultrasound if we also already have chest X-ray? So we see a couple of advantages. Could you please go to the next slide? The first one is that ultrasound is highly portable. So even if chest X-ray is already portable, ultrasound, we use a handheld device, so it's even more portable. It is potentially affordable. It does not use in any radiation. It could be performed at the bedside, so really next to someone at the bed. It could potentially give fast results. And you do not need sputum or any lab infrastructure. Then I would give you some background on what ultrasound exactly is. So ultrasound are very high frequency sound waves, and they could, for example, reflect at any object. So for example, a rib. Then some objects that you would see in lung ultrasound is ribs, so bones, which absorb sound waves. So that's why you would see a large shadow behind a rib. There's also a lot of air, which reflect a lot of those sound waves. And that's why you see horizontal lines in your ultrasound image. There could be a pleural effusion, which is black. So all fluid is black in ultrasound. And soft tissue, it partially reflects and it partially lets all waves through, or let some waves through. So it results in different gray tints. For example, in this air-pleura interface, there's a lot of reflection, which causes these A lines, they are called, horizontal lines. You also see them in the lower image. And they are caused by reflection of the sound waves by the pleural line, and they are also reflected by the ultrasound transducer, resulting in different horizontal lines equally spaced in the image. Thank you. And in this ultrasound image, it's an actual ultrasound image. You again see the ribs causing a large rib shadow. There are 2 ribs in this image, and then a pleural line in between the 2 ribs, and A lines, those horizontal lines below the pleural line. However, there are some challenges in using ultrasounds. And the largest challenge is that there is a lot of air in your lungs, which makes it difficult to visualize deep structures within the lung. Secondly, it relies a lot on artifacts. So you are not really looking at structures inside your lung, but you're mainly looking at artifacts that occur. Thirdly, it has a limited field of view. So instead of making one chest X-ray, you would need to make multiple ultrasound scans. And there is a lot of operator dependency. Next slide, please. And to correctly read the data and acquire the images, you do need some experience, and this is not generally available. So for example, on the left, you see a normal ultrasound video, and you see again the ribs and rib shadows and the pleural line, A lines. Whilst on the right, you see an abnormal video where you do not see a continuous pleural line anymore. So you see some discontinuous pleural line indicating some consolidation. And in the second video on the right, please, next slide. you can see a large pleural effusion, which is black, what I told you before. Next slide, please. And to overcome these challenges, we think that a standardized protocol could be used, as can be seen in this image, in combination with artificial intelligence. Next slide, please. So for that, we built a mobile application, and this mobile application includes the standardized protocol, and it could also include a AI model that will then run offline in this application, and it will give offline results within a couple of minutes. And a novice ultrasound user could then be trained shortly and uses this standardized protocol following those sweeps that are indicated in the mobile device. And then it follows the complete protocol, and it could get a likelihood score for lung abnormalities after completing this whole protocol. Next slide, please. Then we did already train a model which detects normal versus abnormal based on the ultrasound labels that are given by the radiographer. And then this radiographer was shortly trained and acquired the data and labeled the data. And on the left, you see a ROC curve. So for the persons who do not really know what an ROC curve is, it shows how good the model is in detecting, in this case, abnormal lung zones at different thresholds. So the orange line in this figure, it indicates a random prediction, and then the blue line shows the performance of the AI model. So the more to the upper left corner of this ROC curve, the blue line will be, the better the model will be. Then the x-axis, it represents the proportion of normal lung zones that the model wrongly classifies as normal. So how often it gives a false alarm. And at the y-axis indicates the proportion of actual abnormal lung zones that the model correctly identifies as abnormal. Then each point on this ROC curve, it corresponds with a threshold value. And for one of those points, I made a confusion matrix, which could be seen on the right. So for example, from all abnormal lung zones, the bottom row, 74% of those cases were correctly predicted to be abnormal. However, this model now predicts a likelihood score of abnormalities for one ultrasound zone. And what is clinically more relevant is, of course, a likelihood score per person. So for that, I show the results in the next slide. So for this, I took, if one zone is abnormal, I took the score for that complete person as abnormal. So that needs to be at least one abnormal zone. And for that case, you again see the ROC curve, which has approximately the same area under the curve, indicating the same performance approximately. And now you can see, for example, for the abnormal cases again, that if the radiographer gave an abnormal label to at least one of the lung zones from one person, in 97 of those cases, the model also predicted one of those zones for that person to be abnormal. So I hope you enjoyed listening to my presentation. And I would like to thank you and come back to Katja.